And here we are with part 3 of the final exam review for Math 114 Trigonometry. For posterity's sake, this is in the spring semester of 2024. Again, this is part 3 of the final exam review. So part 2 should have just left off with number 13, where we were reviewing over some polar coordinates. To add one last element to that, we found that our polar point, or the point 5 4 pi over 3, which is in the same location as 5 negative 2 pi over 3, is at that highlighted magenta dot there on the 5th circle out from the origin and at an angle of 4 pi over 3. We found that it was at a rectangular coordinate point of negative 5 over 2 and negative 5 root 3 over 2. So over in the third quadrant, if we were to have just traced that out in rectangular points, that means we would have been going 5.2 units to the left. So 5.2 out this way, and then 5 root 3 down, 5 root 3 over 2 down. This is a length of negative 5 over 2. If I zoom in right here, negative 5 over 2 and negative 5 root 3 over 2 would be those two lengths. This is still just following those points out left and right and up and down, as we do with our rectangular points. Moving on to number 14. We're going to solve for the cosecant of the tangent inverse of negative 21 over 20. And here it is helpful to remember, anytime we take the inverse trig function of a number, our result is going to be an angle. So when we're asking for the cosecant of the tangent inverse of negative 21 over 20, we are really after the cosecant of some angle, which I'm going to call alpha. We know from our definition of cosecant that we're going to be looking for the hypotenuse divided by the opposite side. Right? It was just the reciprocal of sine. So hypotenuse over opposite. And we could use a reference triangle to figure that out. So that's exactly what we'll do. I'll just add in some coordinate axes over here, measure in a triangle. I know that I'm taking the tangent inverse of a negative number. So my reference angle should be placed in the 4th quadrant. Again, tangent inverse of a negative. I know that's going to be in quadrant 4. Quadrant 4 for this guy. So this angle right here, that angle measured backwards from standard position, must be our alpha. Then we know that tangent is negative 21 over 20, so opposite over adjacent. We should have a 21 for the y side, 20 for the x side. Opposite side is 21, adjacent is 20. And because we're in the 4th quadrant, the negative sign belongs on our opposite side, belongs on the y value. So negative 21 and positive 20. We have a hypotenuse that we're going to want to solve for. Solving for a hypotenuse means going to the Pythagorean theorem. So we're looking at c squared being equal to 20 squared plus 21 squared, which will be 400 plus 441. Adding those up, we get 841. And then taking the square root of 841 should get you 29. So C is 29. Because it's a hypotenuse, we don't need to bother with a plus or minus. The hypotenuse of a triangle is always positive. So 29 for the hypotenuse. Which means the very last thing we need to do is come fill out our fraction. We know our opposite side was negative 21. That part was given to us. We just needed the hypotenuse in the numerator, and that was 29. So our answer to the whole thing should be negative 29 over 21. And that solved our problem. On to the next. Finding all solutions for theta in 0 to 2 pi. So all solutions that solve the following trigonometric equation that are within one circle. So we don't need to loop around more than once. We could find other solutions located in full spins around a circle and then still stopping in the same direction. But we're going to limit our answers to being between 0 and 2 pi. The other way we frequently solve this problem would be looking for all general solutions. I think we'll see that in the next problem, which is where we add the 2k pi and leave that as part of our answer. But for this one right here, we'll just solve for all solutions between 0 and 2 pi. So let's take off from there. Looking at the equation, I've got cosecant squared of theta minus 7 cotangent theta minus 9 is equal to 0. So right off the bat, I've got more than one trig function within my equation, and I'd like to reduce that count to make it a little easier on ourselves. So I am going to start by trying to get everything in terms of cotangent, since that's the trig function that is not squared. Fortunately, this cosecant squared I know is part of a Pythagorean identity, namely cosecant squared is equal to 1 plus cotangent squared of theta, with the rest of the problem remaining the same. 7 cotangent theta minus 9 equal to 0. And now I only have one trig function. It's cotangent showing up twice. Granted, there's a cotangent squared and a cotangent to the first power, but we can resolve that by factoring our equation. So combining some like terms first, I have a +1 and a -9. I'll simplify that to -8. And now this quadratic equation is factorable. I'm looking at cotangent of theta -1. Or I guess that's really +1, isn't it? Cotangent theta +1 times cotangent theta -8 equal to 0. Right? I need a factor pair that multiplies to 8 but adds to 7, or adds to -7, I should say. So that factor pair is going to be -8 and 1. From there, I can separate out these two factors using the zero product principle to say that either cotangent theta +1 is equal to 0, or cotangent theta -8 is equal to 0. One of those two must be true in order for this equation to work out. I'll create a little bit of extra space here. Just to be clear that these are two different paths we'll be going down. Along the left side, I've got cotangent of theta must be equal to -1, and that happens twice within the unit circle. And for this one specifically, I can go directly to the unit circle to get my answers. I'll be looking for angles that are in the second and the fourth quadrant, since that's where cotangent is negative. And if cotangent theta is equal to -1, my two angles are 3 pi over 4 and 7 pi over 4. I'm just going to go ahead and add those to the box right now. 3 pi over 4 and 7 pi over 4. All right, I know I'm looking at a class of the pi over 4 angle, since cotangent is equal to 1 or -1. And again, wanted to pick out the two that were in the second and the fourth quadrant. Now, working at the other side, the right side, I'm looking at cotangent theta being equal to 8, which means that I could be solving tangent of theta equal to 1 over 8. Now, I've switched to tangent here because I can see that 8, or 1 over 8, neither of those are a value that we know off of the unit circle, at least from the 16 points we have memorized. So we're going to end up needing an inverse trig function here. In order to solve for this thing, we'll need to find a reference angle and use that to solve out the rest of the problem. And since we don't really work with cotangent inverse, switched it over to tangent, so we could solve for our reference angle in terms of a tangent inverse function. So coming up here to the space, spot where I have space, I'll say that my reference angle for the right half of the equation is going to be the arctangent or the inverse tangent of positive 1/8. Here I'd be taking an absolute value of that 1/8 if I needed to, but it's already positive, so I didn't need to worry about it. Plugging that into a calculator and being in radian mode, you should get 0.1244, or at least that's what I got. So that's our reference angle. Using our reference angle, we'll need to locate the two angles within one circle that solve the equation. So come back to the original statement of tangent theta equals 1/8. That number is positive. So we should be finding solutions that are in the first and third quadrants. Those are the two quadrants where tangent is positive. So label that up here. Quadrant 1 and quadrant 3. A little bit more clear. 3. We'll need equations for those two quadrants. First, in the first quadrant, our solution angle is just equal to our reference angle. So our reference angle actually solves the problem this time. It's 0.1244. Be careful with that because the reference angle is not always a solution angle, but it did work out in this case. I'll just add that to the box, 0.1244. I know it's an answer now. Our other option in the third quadrant, we know that our solution angle is equal to the sum of pi and the reference angle. Remember that all of these solutions are going to be based on the reference angle. But I'll just take pi, add in the number that we got for our reference angle, 0.1244. That's just a calculator problem. I came up with 3.2659. 3.2659. And that should be it. Those would be all of our solutions. 4 angles all together that solve the original equation. The next problem down is going to ask for all general solutions for theta. So this time we are not limiting ourselves to just being stuck between 0 and 2 pi. So we'll instead get our solutions in terms of plus 2k pi and leave that as our answer. So again, this find all general solutions for theta means we're looking at all solutions between 0 and 2 pi, and then anything coterminal to those solution angles. So anytime we see all general solutions, we know that we should have a plus 2k pi as part of our answer. That plus 2k pi simply means anything coterminal to the value that gets attached to will also solve the equation. So we're going to add 2k pi to all of our solutions. Other than that, the beginning of the problem looks fairly similar to the one above. This one comes pre-factored, which is nice. So I'll just separate it out into those two spots. One is a cosine theta equals 0, which means theta itself is pi over 2 or 3 pi over 2. Pi over 2 or 3 pi over 2. And again, we want to make sure we're adding 2k pi to both of those. So pi over 2 plus 2k pi and 3 pi over 2 plus 2k pi. Anything coterminal, one of those guys will solve the problem. Or on the other side, we also have sine of 5 theta plus 1 is equal to 0. Which means we're looking at sine of 5 theta being equal to -1. Bring that just back to the left a little bit. And I've got this 5 theta here that keeps showing up. Right, that 5 theta that's on the inside of sine. So I'm going to deal with that after I start by just solving, say, sine of y equals -1. Right, so just think about on the unit circle where I can find solutions for sine being equal to -1, and that's going to happen at 3 pi over 2. That's the angle on the unit circle where sine's equal to -1. So I know that that needs to be part of my solution. I'll just have to work it out from there. But I'll start from 3 pi over 2. I know that anything coterminal to 3 pi over 2 also solves the problem. So I'm going to add 2k pi in right here. And now I'm going to turn my attention to the fact that I had 5 theta on the inside of sine instead of just theta. So that means to figure out theta itself, I should just divide both sides by 5. So if I've got some space here, or do I want to simplify this work? I've got an idea. I'm just going to move some of my notes around slightly. I've got more space on the left half of the page. There we go. Why don't we just move this to be here and here. Take this guy and slide it over to the right half of the answer box. Cool. And then that'll give me enough space to divide both sides of this equation by 5, giving me a 3 pi over 10 plus 2k pi over 5. And then I'll add that solution into the box as well. So 3 pi over 10 plus 2k pi over 5. I'll keep highlighting that guy with magenta. There it is. Got the whole thing that time. So those 3 equations, those 3 pieces, all solve for theta. That'll again give us equality in the original equation. Any one of those 3 expressions, I'll solve it out. And looking at 17, now we're moving into some of the exam 4 material. So we're going to be given a pair, or we're going to be given information about a couple of angles, an alpha and a beta, and we're going to use that information to first find sine of alpha plus beta, and second to find the cosine of beta over 2. So we'll be using a sum formula for sine and then a half angle formula for cosine. So we'll just try to put that all together here in a moment. First things though, I am interested in finding reference angles for both of alpha and beta. So let's start by putting that together. I'll grab a coordinate axis. And then I know I'm going to need 2 of these, so why don't I just copy and paste it? Once for alpha and once for beta. So looking through alpha, I'll do that angle in red. I'm told that secant is -17 over 8, and sine of alpha is positive. So secant, it's the reciprocal of cosine. It's going to be tied to the x value. I see that secant, or x, is negative, and sine, or y, is positive. So I need to be on the left because x is negative, and I need to be on the top because y is positive. So if I go left and I go up, that gets me into the second quadrant. So I'll make sure to draw my triangle up here in the second quadrant. That means that alpha is going to be this angle over here, measured from standard position into the second quadrant. Secant of alpha is negative 17 over 8. Secant being hypotenuse over adjacent. So 17 for the hypotenuse, 8 for the adjacent side. We're in the second quadrant, so the negative should get attached to the x value. And then we'll set up a Pythagorean theorem to get our missing side y. We should find that it is 15. 17 squared minus 8 squared. And will get us to 15. Up next, before I go to draw the triangle, let's figure out which quadrant we should be in for beta. Beta, we're just actually given an inequality for the angle. We're told it's in between pi and 3 pi over 2. That is describing the third quadrant. So I should just be able to draw my triangle in the third quadrant right away. Let's try and get that so that it lands right in the center. I suppose we'll consider that close enough. And what were we given? Tangent of beta is equal to the square root of 15. Normally, it's nice to have a fraction, since we know we're going to be setting some ratio up for tangent. If we just have a single number that tangent is equal to, we could just call that square root of 15 the same as square root 15 over 1. And then when we go to say, all right, tangent is opposite over adjacent, we can give a square root 15 to the opposite side and a 1 to the adjacent side. And then because we're in the third quadrant, both x and y should be negative. So I'll attach negatives to both legs. I know that beta is going to be this angle right here, measured from standard position over. I'm just missing my hypotenuse. 1 squared plus root 15 squared, that's 1 plus 15 is 16, and the square root of 16 is 4. This was just right over here. Maybe should write out the Pythagorean theorem that I was using. This is y squared plus 8 squared is 17. And down here we had 1 squared plus 15 is c squared. It should be a little more clear on that. This is the review for the final exam. This is square root 15 squared. All right, then we need to go to the first thing that we want to solve. Sine of alpha plus beta. If we just check our formula sheet for the sine sum formula, we'll see this is sine alpha times cosine beta plus sine beta times cosine alpha. Where we'll grab those two angles from the red and these two angles from the blue. So I need a value here, plus a value here, times a value there. And we'll just go to our reference triangles to get them. The sine of alpha, opposite over hypotenuse, that's 15 over 17. And while we've got red out, let's also get cosine of alpha. That's negative 8 over 17. Switching over to the blue angle, I know the cosine of beta is negative 1 over 4. And the sine of beta is negative root 15 over 4. Now we're going to want to just multiply that stuff across. Maybe create a little bit more space here. Multiplying all that stuff across into just a single fraction. So I don't anticipate this one's going to be too rough. 17 times 4 for our denominator. I believe that's 68. But across the numerator, 15 times 1 is 15, plus negative 8 times negative root 15 becomes plus 8 square root 15. Ooh, I've missed a negative sign here, didn't I? Yeah, 15 times negative 1. There we are. Negative 15 plus 8 square root 15, all divided by 68. And next, let's come evaluate cosine of beta over 2. Starting with what we can get from our formula sheet, we know that cosine of beta over 2 should be plus or minus the square root of 1 plus cosine of beta over 2. And that beta was the blue angle that we've been working with. Right, that's all from our formula sheet. And let's section off this problem into a couple of pieces here. Maybe, and I want to draw right at the equal sign, don't I? Sort of think of it as a left half and a right half of the problem. On the right half, the inside of the square root, all of that depends on beta. The reference triangle that we already drew, we know we can just scroll back up to the top of the page and get that information. First part I'm interested in, though, is that plus or minus on the left side, the outside of the square root, because that's all going to depend on the quadrant that beta over 2 is located in. Right? So if I want to know the sign, the plus or minus sign on cosine beta over 2, I need to know the quadrant that angle beta over 2 is in. So I had an inequality for beta, and I'm going to start by working with that. Back at the beginning of the problem, I was told that beta itself is in between pi and 3 pi over 2. And since I want to know a quadrant or an inequality for beta over 2 instead, I'm going to multiply this entire thing by 1/2. Meaning that I'll have that beta over 2 is in between pi over 2 and 3 pi over 4. That puts it squarely in the second quadrant. In fact, it's in the early part of quadrant 2. We could say that. But all that really matters is that we're in the second quadrant for beta over 2, and in the second quadrant, cosine is negative. So I want to take the negative value off of that plus or minus. And then I can keep solving the inside like normal. So on the inside, I need 1 plus cosine of beta over 2. All over 2, I should say. So we'll scroll back up to our original reference angle for beta and find the cosine value. It's looking there in the upper right. Cosine of the blue angle, that's negative 1 over 4. Negative 1 over 4. And we'll solve this guy out. I've got too many denominators, so I'm going to multiply top and bottom by 4 to get rid of the extra denominator we've got going on. This thing looks like negative square root of, well, I'll have 4 minus 1. 4 minus 1 all over 2 times 4. All over 2 times 4, which is 8. And start to simplify this. I'm looking at the square root of 3 divided by 8. And in an effort to simplify this thing as much as possible, I'm going to multiply top and bottom by 2, just so that my denominator is a square number. So that'll be, don't forget the negative sign though. Right, that negative sign is kind of important. We spent a lot of time getting it, so we should make sure we keep it with us. In the top, underneath that square root, I've got 3 times 2, which is 6. And in the denominator, 2 times 8 is 16, the square root of which is 4. So negative 6 over 4. If this thing were a multiple choice problem, this would be the multiple choice answer that I would have provided in the box. The other intermediate steps along the way wouldn't be present. So I wouldn't have put negative square root 3 over 8 in the multiple choice answer box. I'd put negative square root 6 over 4. So you just need to be able to identify that as the correct answer. Right, on to number 18. We've got a ship traveling 58 miles due east. That's then going to adjust its course to 72 degrees east of north after traveling 89 miles in this direction. How far is the ship from its point of departure? And include a fully labeled diagram showing bearings and all that kind of fun stuff. So let's do that. Starting with this ship's path. It is going to travel due east, which is a bearing of, what's a heading of 90 degrees. But as a bearing, it's just a horizontal line, right? Goes directly to the right because that's east. Don't forget to never eat soggy waffles. We're headed east. We're going this way. So I'll draw that diagram in. Now, that means it's going to start out here at point A. We'll just use A, B, and C to represent the various points of this ship along its journey. It's going to travel out to some point B, which is where it's going to change its heading. I'll put B in right there. I'm going to leave a little bit of space on the edge of my line, but I'll say that this first distance right here is 58 miles. I've got 58 miles in between points A and B. And actually, so that I've got enough space in this diagram looks a little better, I'm going to bring those a bit closer together because our next distance needs to be a fair bit longer than B. Right, I think we're going to be going 89 miles in some new direction. So we're going to adjust our course to 72 degrees east of north. So I'd start at north, measure 72 degrees over to the east. My ruler, I think, should have a remainder value of 18. At which point, the ship is adjusting its course here and traveling for 89 miles. So just make sure that that distance is longer than the first. There's only 58. So this is 89 miles. And distance over here between points A and B is 58. I'm going to darken in that part of my line. Be clear that that's what we're talking about. Put B back on top. All right, so at the end of that line up there, I'll call it point C, because that's where the ship ultimately ends up. And the part that we're after is how far the ship is from its original point of departure. We could just add 58 and 89 together, and we'd get, what, 147 miles? That's how far the ship has traveled. It's following it along. But it's a little bit closer to its initial destination than 147 miles. Since if we take the straight line shortest distance between the two, we would draw in this line I'm hopefully going to get right here. See, is 11 degrees closest to connecting the 2 points? Yes, it is. All right, so let's draw that line in. So that's the distance we're going to be interested in solving for. Looking at the way that we've written in our diagram, that is going to be side length B. And we can color in our other two side lengths. This 58 is length C, and this 89 is length A, since those are the angles that those sides are opposite. So let's finish labeling what we know, because there's one last piece of information that we have baked into our diagram, but that we haven't labeled just yet. Namely, we haven't labeled our bearing angle. So we were told that the ship adjusts course to 72 degrees east of north, which means that this purple angle right here is 72 degrees. That's our bearing angle. Remember that bearings should always be measured from due north or due south. Somehow I tried to combine north and south together, and I think I came up with sorth. Not an actual direction, kind of like west. Yep, so this one's measured from north and then over to the east, 72 degrees over to the east. So that's our bearing angle, but it's not actually the measure of angle B, so be a little careful with that, because angle B, the one that is inside of this triangle, should be this blue arc right here. All right, one more time to get a decent looking arc. Oh, close enough. Nope, I'm apparently being stubborn. I'll be here all day, just trying to draw in one satisfying arc. All right, I'm gonna leave that alone for now. So we also know that this angle right here is a 90-degree angle, since it is connecting. I'm apparently not quite satisfied. All right, I need to leave this alone. I don't know why it keeps bumping right there. It's like my screen's uneven. Huh. All right, so that's enough. We know that's the right angle because we're connecting from heading east to a line that goes due north. So that'd be a 90-degree turn, meaning that if we wanted to get the measure of angle B, which we do, B ought to be 90 degrees plus 72 degrees, giving us a result of 162 degrees. And now we actually have enough information to get B right away. This thing is an oblique triangle, meaning that our usual SOHCAHTOA and Pythagorean theorem do not apply because it's not specifically a right triangle, but law of sines and law of cosines would. Now, specifically here, we know length A, length C, and angle B. So we know two sides and the angle that's in between them, making this thing a side angle side triangle. So we'll go to the law of cosines. And the unknown here is side length B. So we'll use the version of the law of cosines that puts angle B into the cosine at the end, since that's the one angle that we know. Right? I know angle B, so I'm going to use the version of the law of cosines that has angle B in it, which looks like B squared is equal to C squared plus A squared minus 2CA times cosine of angle B. And then we just need to plug stuff into that. So b squared, that's our unknown. It's equal to c squared plus a squared minus 2 times c times a times the cosine of angle b. So we'll just plug all of that in. C was 58. It goes here and here. A was 89. It goes here and here. Angle B, 162 degrees. That's what we're plugging into cosine. And from here, that's all just a calculator problem. Plug all that in. Once you're done, take the square root of that number. I got 145.27 miles. So remember that we said at the beginning, the ship had traveled 58 plus 89, which is 147 miles. If we look at its two legs independently, that's how far the ship itself has traveled. But at the end, it's going to be less than 147 miles away from its starting location because it didn't spend the entire time moving exactly away from point A. So we knew this number should be less than 147, but not much less, because that course correction that we made, that new bearing we took, was pretty similar to our original heading. We adjusted from 90 degrees east of north to 72 degrees east of north. Not a big change in direction. So that number, I think, makes sense. That's what I'm arguing for right there. And lastly, I think this is our final problem of the review, problem 19. We have a woman entering an outside glass elevator on the ground floor of a hotel, glances up to the top of the building across the street, notices the angle of elevation is 48 degrees, then rides the elevator up 3 floors, or 60 feet, finds the angle of elevation to the top of the building across the street is now 32 degrees. Our goal in all this, figure out the height of the building across the street. So this will require a pretty good diagram to figure out exactly what's going on. So we draw in the ground floor, which will be a horizontal line. Just draw on the ground. It's at 0 degrees. It'll be nice and level. There we go. Draw in my ground real quick. Right there. And there's a building across the street that we are hoping to find the height of. Let's fill that in a second. First, a woman's going to be riding up a glass elevator. Let's just put her here on the left. Elevators move straight up and down. So how about we call this vertical line over here a glass elevator. From the bottom, she's going to measure an angle of elevation of 48 degrees. Remember that angles of elevation are measured from horizontal lines. So my ruler will match 48 degrees over here. She measures that angle of elevation to be 48 degrees right here. She then is going to ride the elevator up 60 feet. So if we kind of imagine what's happening here, she'll start on the ground floor at the bottom of the ruler. She'll then ride it up 60 feet. Get 3 fours above. And we're going to measure a new angle of elevation from that 3rd floor. Get it maybe a little bit of a longer side here. Right. So the woman is riding up to that distance, or to that point. We'll just label in a 60 right there because she's going up 60 feet, and measures a new angle of elevation. This time it's only 32 degrees instead of 48 degrees. So I'll draw in a new line, new angle of elevation right here. Looks like I didn't quite draw the first one long enough. Let me just extend that slightly. All right, And there we are. So those are the two angles of elevation measured by this woman riding a glass elevator. First one, from the ground, was an angle of elevation of 48 degrees. 48 degrees. The other, measured from the third floor, was 32 degrees. And again, we know that there's 60 feet in between the two floors. Now, I'm just going to grab my diagram and move it down a little bit so that it's not intersecting the words of the problem, just make it a little bit more clear. Said, supposed to move it down. I should probably move it all the way down then. Get it out of the way of this stuff too. Right. All together, where those 2 points intersect, that must be the height of our building across the street. So I'm going to call this one point B for building. And now that I know where it should be drawn, I will draw that building in. So this must be what our building looks like. I'll even fill in the other side because, why not? Cool. So here is our building. 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 Cool. This building has a height of h. And looking at what I know right now, I could set up an equation here. I need to finish labeling my sides though. So if I'm calling point B up there in blue, the side opposite it is this 60 down here. I'm going to mark it in blue as well. We started from the ground, so I'm going to call this guy, call that point A. And then the remaining point will be C right there. And the side opposite C is this green side right here, the one that's connected to the 48-degree angle right now. And that side forms a hypotenuse of a 48-degree right triangle, where the side opposite the 48-degree angle is the height of the building. Meaning, I could use just a regular old SOHCAHTOA equation, say that the sine of 48 degrees is equal to opposite over hypotenuse. So it's equal to h over c. H over c. Fill in some of that stuff. So we've got an equation that'll get us the height of our building. All we'd have to do is solve that thing over for h, and we're good to go. So why don't we just start by trying that? Bring that down here so we can still see it. The height, the thing that we're interested in finding, h, it's equal to c times the sine of 48 degrees. There's just one problem, one snag that we run into, and that's that we don't know the value of c. At least we don't know it yet. We could probably solve for it, but as of right now, c is an unknown. So we're going to need to figure out c. We need to know the length of the hypotenuse of that right triangle before we could find the height of our building. Now, in order to have enough information about c, we're going to need to solve the oblique triangle that kind of sits on top of that right triangle. So the very first triangle drawn in, like this guy right here, right? That's the triangle that I'm going to want to solve. That's the one where I'm going to be able to figure out the value of c, and then I'll use that value to go over to the right triangle and find the height of the building. So this thing becomes an oblique triangle problem, which means we'll be relying on either the law of sines or the law of cosines to get there. So we should finish labeling in what we know about that triangle. So far, we only have one side length written down, and that's it. We know that that vertical side length B is 60 feet. We have not yet figured out angle A, angle C, or angle B. So let's start at least labeling those within the triangle. This red angle here is going to be angle A. And you might have already noticed that that has a measure of 42 degrees, since it's going to be the complement to 48. We'll also need to come up here and get angle C. There's actually this green angle right there. Notice angle C is not 32 degrees. Also, angle A is not 48 degrees. Both of those are angles of elevation, but they don't translate directly to the triangle that we're looking at. They're just going to be related to them. So we'll label those two angles on there. And then finally, we'll come up here and get angle B as soon as we have enough information for it. So let's go into our workspace and start solving for these. We know that angle A should be the difference between 90 degrees and 48 degrees. Since those two guys together need to make up a right angle. We already wrote that one down. It was 42 degrees. Next, we'll get angle C because we know it's related to one of our angles of elevation, but isn't exactly equal to it. So angle C, that must be the sum of 90 degrees and 32 degrees. Since if we look at the way that angle C is constructed, we go from our line that's going straight up in the air all the way up to that diagonal line, that 32-degree angle of elevation to get to point B. So looking at angle C altogether, it's 32 degrees plus the 90 degrees below it. So adding those up, I believe we get 122 degrees. I'm running out of space in the diagram, so I won't label it in there because it'll get kind of messy. But now that we have those two angles, getting the third angle in our triangle is a piece of cake. We know that they just have to add up to 180 in total. So B should be 180 minus each of the other two angles. So 180 minus 42 minus 122, 122. I believe you'll get 16 degrees. So angle B, we knew that was a smaller one, just based on the diagram that we drew, only 16 degrees. Now we know all three angles. We know one of our side lengths. We could use the law of sines to figure out our missing side length. So let's do that. The side length we really wanted to know was C. So I'm going to put it up in the numerator. C divided by the sine of its angle, which is 122 degrees, should be equal to side length B, which is 60, divided by the sine of angle B, which was that 16 degrees. Solve that thing around for C. Just shrink that down a tiny little bit so I've got space to write. C is going to be equal to 60 times the sine of 122 degrees divided by the sine of 16 degrees. Add a splash of color in here. Both of these values were from B. And now that I know C, I can finally come back up to the original thing that we were trying to solve for, the height of that building across the street, H, and just plug in C. I know that C was 60 times the sine of 122 degrees. I know I'm multiplying that into the sine of 48 degrees. So that was part of the equation already here. And then all of that gets divided by the sine of 16 degrees. Still coming over from our substitution for C. Bring that right here. Because then in the final step, we'll just plug all that into a calculator to get 137.19. 137.19. And that's in feet. Just to further illustrate what I was doing here, we were taking length C from here and plugging it into this guy. That was our substitution. And with that, I believe we've completed the final exam review. The very last page on here is a formula sheet, one that I suggest you have ready as you're taking the final exam. So if you've made it this far, you're probably watching this before the exam. Again, remember, this is a video for spring semester of 2024. So if you happen to be watching this in a different semester, this information might not be accurate. But as long as you are preparing for your final that's on Tuesday, April 23rd, this information will be accurate. So you know that this exam is online. You should take it on D2L. You have access to all of your notes on this exam, so it's all open note. Bring whatever you like with you. So I won't be attaching a formula sheet like this one, but I do recommend that you have this one ready and available. Since it's got all of those formulas we haven't been memorizing right here at the end of the semester. Right, there's a ton that's on here. Law of sines, law of cosines, sum and difference, double and half. All that shows up on this formula sheet. So I'd recommend having that handy as you're taking the thing. And again, the exam's about 2 hours long. I mean, you get 2 hours to take it. I suspect some will finish in less than 2 hours. Some might end up using that entire 2-hour time. But it's 2 hours from whatever point in time you start the exam. So if you start the exam at, say, 10 a.m., it'll finish at noon. That is our course's official time slot, is Tuesday from 10 a.m. to noon. So you can take it there if you're pressed for time. But since our exam is just online, I figured, can't hurt to have it open for the whole day. So you can take it whenever you like, but again, our official time is 10 to noon. But as long as it's in by midnight, you should be all good. And with that, I think I am going to end the review here. So probably didn't introduce myself at the beginning, but for one last time, I've been your host, Steve Dragoo, signing off.